If you are a scientist and you say that hollow Earth is impossible because of observational data, you're just a bad scientist. I'm sorry. Greetings, this is Eugene the Philosopher, the greatest living philosopher after the unfortunate passing of Quentin Robert de Nameland, who has been the greatest living philosopher before me. In this video, I wish to make a case for the hollow Earth, and also maybe tentatively about the expanding Earth, but we'll see. Actually, you know what? Without further ado, let's begin. Alright, let's go. So first of all, I want to advertise my video made like 4 years ago, basically 4.5. And the video is about my paper. I'm gonna link all the links in the description, by the way, like everything I'm gonna show you, all this horrific monstrosity that you can see in my tabs, you will see it in the description as well, so you can check everything out. So this is a paper of mine which deals with a possibility that a subsurface biome, that is microorganisms or whatever, may actually cause earthquakes. This is just, I mean, since we're dealing with the Earth's interior, might as well mention that. Okay, so let's start with hollow Earth, right? Well, first of all, I want to mention like how recent all of our understanding, or understanding in air quotes if you wish, of the Earth's interior is. Like in particular, the concept of the existence of the outer core was only proposed in 1906 by Richard Oldham. Then the existence of core mantle boundary, or CMB, that's not cosmic microwave background by the way, was proposed in around 1914, and it's called Gutenberg discontinuity. Then we have the idea of Wegener's continental drift, which was proposed in 1926 or about so, and right about here, look at this. In case you don't know, like Wegener was incredible, like he basically was ridiculed for his ideas, right? Like, why are you telling us the continents drift? Are you crazy or something? So basically our current geology, like its main idea, the continental drift, it was widely criticized. Like it was like it took a while before people accepted it, and it makes it kind of ironic, right? Like Palpatine, you know, meme, ironic. That people criticize alternative concepts of the Earth's interior, such as hollow Earth. So that's why I'm mentioning it here. So out of all people, you would expect geologists to be kind of like more open to alternatives, because again, our current geology actually stands on one of these alternatives, so to speak. At least it was an alternative less than 100 years ago. Regardless, let's talk about hollow Earth proper. So first of all, what I need to say is that we have no direct observational evidence for literally quite anything, you know, in the Earth's interior. So whether it's hollow, whether it's not, we have no clue, because again, humans have only been as deep as 2.1 kilometers. That's like the deepest cave located in Georgia. That's the country of Georgia, not the state of Georgia, just FYI. So again, I'm gonna link all of this so you can check it out if you wish. Then we have drills operating at sea, for example. They've been able to drill as far down as 2.1 kilometers below the surface. It was done by this little babe, okay, this ship. Then the Kola super deep borehole on land was able to get as far down as 12.2 kilometers, right? You probably know about this. So it's basically nothing, right? Basically nothing. So point is, we have no knowledge, right? We cannot directly falsify or verify any claims about the Earth's interior. That's my point here. So in case you agree, let's go on. We're only left, therefore, with secondary or indirect evidence. And here, I want to consider seismology and magnetic field mostly. So any geologist will tell you, hey, we have plenty of seismology data, so we know the interior of the Earth pretty well. And my point here would be that no, we don't, okay? Like hollow Earth does not contradict any seismological data, as far as I'm aware at the very least. Again, if you have some data which cannot be explained by the model I'm going to present to you, you're welcome in the comments. And magnetic field, and then we'll discuss like some related or maybe not even related things, okay? So seismology, like why do we think we know the Earth's interior really well? Why do we know, I mean, we think we know there is no cavity inside the Earth, okay? Well, they say, okay, so let's assume some energetic process happens. It could be an earthquake, it could be like a nuclear test, or something like that, like something with a lot of energy to kind of shake all of the Earth, okay? So just let's talk about earthquakes for simplicity. And all of earthquakes, by the way, occur not deeper than 700 kilometers. So that would be about 1/10 of the Earth's radius. So this would be like as deep as here-ish, something like that, maybe. So this picture is very general in this respect. Okay, so we have S waves, which are shear waves, transverse waves. It doesn't actually matter, but I mean, since we're looking at this, I might as well explain it to you. And P waves are like S means secondary actually, and P means primary. So S waves are shear waves, and P waves are compressional, like longitudinal waves. Okay, so people say, okay, we have a liquid core, and it does not, I mean, liquids cannot transmit transverse waves. That's why S waves are only observed about to here, 103 degrees. That means, like, if you measure this angle between this point and this point, so this angle would be about 103 degrees, which is understandable. But as you can understand, I mean, if we just delete the outer core with the inner core and say we have a hole over here, then the picture is exactly the same, okay? So it doesn't contradict the hollow Earth. All right, let's take a look at P waves then. They can be transmitted through liquids, right? So they can go through the inner core, the outer core, and that's what you observe here, these purple lines. So this would directly falsify indirectly falsify the hollow Earth idea, right? Because if we have a hole here, like, nothing can transmit these waves. And I would agree with you, unless we consider this little thing, like, why are they curving like this? And this curving is a refraction, okay? Why does it happen? Well, it happens because the layers of Earth supposedly have different density, and therefore, also different elasticity, but let's just talk about density for simplicity. So the denser the matter is, the higher, again, as a general rule, it's not always like this, but as a general rule, the higher is the velocity of propagation of seismic waves, okay? It's kind of the same with light, by the way, so it's almost like an optical problem we're solving here. Almost, again. Don't take me literally. So, this is the pattern of refraction of these waves. So they tend to curve away from denser regions, okay? For simplicity. Again, it's actually regions with higher speed of propagation, but let's just call it denser regions for simplicity. All right, and that's why hollow Earth is viable, because there is a guy called Jan Lamprecht. There was a video of him on YouTube, which I haven't found, because, like, I've watched it, like, the first time I've watched it was like 10 years ago. As you can see, it was from 2003, actually. He has a book. I've never read the book. I do have it, but I gotta admit, I've never read it. But I've watched the video, and the idea he presents is incredibly elegant and simple. Basically, the idea to explain how you can have a cavity here and still have waves over here, right? So if you have a seismometer here, an earthquake happens here, like, you can still detect something, right? And the idea is very simple. It's like, we're saying, okay, let's assume, I'm gonna link all of this, as I've said, so you can watch it. It's a very good lecture, not a lecture, I mean presentation. So let's assume that the density rises as we go, rises with depth up to a certain point, like it's this circle. It's this certain point that I'm talking about. So the density rises, then after this certain point, as I've called it, it starts falling, all right? What would that cause is that the waves would no longer curve away, but they would curve towards the center of the Earth, because the density near the center is lower now, okay? And that's what causes this sort of pattern of wave propagation, all right? So they curve away from the center, where the density rises, and then when the density starts falling, they curve towards. And as you can see, in this way, you are able to propagate the waves through, so to speak, through, or rather around in reality, this cavity, which may exist within the Earth. That's why we call it hollow Earth, okay? So yeah, this is an incredibly simple and elegant idea, and I really love it, and I think everyone should know about it. And I think with this very simple idea, you can make hollow Earth viable, and I basically see no arguments against it. Like, why not? You know, because traditional, mainstream, as you may call, geology. Or seismology, for that matter, implements so many crutches, like like to refine their model. Basically, that's what I'm saying. So this proposal is very simplistic, but obviously there would be a lot of anomalies that you have to explain additionally, with some additional hypotheses. Let's put it this way. And to this, I might answer, well, mainstream geology also implies all kinds of additional hypotheses. Like, for example, we have this graph of velocity, which looks really weird. So they have to introduce this crutch to explain the patterns that we observe, which doesn't look good, if we are honest. Then they introduce all kinds of stupid kinds of waves, where, for example, P wave is suddenly turned into an S wave and back into a P wave. Like, just look at this. It's just a glossary, you know? It's just a dictionary. It's not even like we're not even explaining anything here. It's just the explanation, like short, brief description of terminology. Like, look at this craziness. Okay, so if you introduce just as many crutches for Lamprecht's model, like, imagine what we could achieve with this. All right. So yeah, it's not like, you know, mainstream geology is super solid, no pun intended. In fact, okay, we've talked about this already. No pun intended, the mantle should be solid because, you know, it should, like, this is the mantle, the orange thing, and, well, to a degree, the yellow thing as well. So it should transmit S waves, right? But if you remember the continental drift, the mantle should be also liquid because continents should, you know, kind of slide on top of it. And it's kind of like what? Is the mantle liquid? Is it solid? Like, can you make up your mind, you know? In the end, they arrive at additional crutch called a asthenosphere. Where is it? Where they say, okay, like the uppermost layer of the mantle is actually liquid, kind of, so the continents can flow, you know, kind of slide on top of it, whereas all the rest of the mantle is solid. Okay, but then again, the question still, like, how can you, you know, transmit S waves through a asthenosphere then, if it's liquid? You know, it's like, it's almost solid, okay? Like, almost solid. You know? So it's almost can transmit S waves. Like, what the hell, guys? Can you make up your mind? Alright, so hopefully you can see that there's a lot of problems with conventional geology, and I'm pretty sure that this model is just so simple. Alright, so if we introduce just as many crutches for it as we have introduced for regular geology, maybe it would be even better, you know. Maybe it would explain everything. Alright, so let's end with wait, let's not end. I wanted to say, like why would possibly density start to decrease? Like, what's the like, you know, physical explanation for this, or at least like intuitive explanation? Well, for example, consider this. So the gravitational attraction, if you assume, like, you see the constant density of Earth, if Earth is just a solid ball basically, then the gravitational attraction rises like this. That's the center of the Earth, and this is the surface of the Earth, the one Earth radius, right? So if we assume a constant density of Earth, the gravitational attraction rises like this, linearly, all right? Which kind of makes sense for the lowermost layers of Earth, or at least, like, we have a cavity around here in our model, like, where we basically delete the outer core and the inner core. it kind of makes sense that if the gravitational attraction is the lowest here, the density would also be pretty low, right? Kind of makes sense. Why would it be any other way around? And look at this, the model, the currently accepted model, right? Like it has this really weird change of behavior somewhere here. And it looks really suspicious, you know? So, yeah. So there is, my point here is that there is a physical, I think, justification for the density to rise and then fall at some point. So it's, in some sense, you may say that the walls of the cavity would kind of resemble the surface of the Earth in terms of density. Perhaps, I mean, it's my hypothesis. Like, it's not guaranteed. And the density on the surface is mostly silicates, right? It's like 2.7 grams per centimeter cubed, or maybe 3, something like that. Or basically the density of aluminum. All right, and since we are here, like, let's talk about density. So the average density of Earth is actually the biggest in all of the solar system. Like, the Earth is actually the densest body in the solar system. It was kind of weird to figure it out, okay? And you may ask, well, okay, if we actually have a huge hole in the center of the Earth, wouldn't the density of Earth, of like matter in Earth, become even bigger because we're we're left with lesser volume? And it's actually not the case. Like, I've made a calculation, and the current density of Earth, I mean average density I'm talking about, is like 5.4 grams per centimeter cubed. And if you make this hole, if you basically remove the core completely, so the bottommost 3.5 thousand kilometers are empty, you only arrive at the density of 6.5. So it's like maybe like a 16%, 17% increase, something like that. So it's not a big deal, okay? It's not an issue at all. This is still lower than the density of like iron. You know, iron is 7.8. So this is the density of like antimony, cerium, I think, some other metals like this. So it's not a big density. All right. So we're pretty much finished with seismology. Let's talk about the magnetic field. So you would say, aha, we have the dynamo theory, which explains, in air quotes, like I'm being sarcastic right now, explains how Earth's magnetic field is formed, all right? And if you don't have anything in the outer core, I mean, supposedly it's the outer core that generates the magnetic field. If you don't have the outer core, how do you generate the magnetic field? Like, it contradicts the dynamo theory. Well, I'm sorry to disappoint you, but the dynamo theory has been directly, observationally falsified. Let me clarify what I mean. There is a theorem called Cowling's theorem, and I will quote, which states that no axisymmetric magnetic field can be maintained through a dynamo action, all right? What does axisymmetric means? It means basically like if your planet is, like if your magnetic pole coincides with your like geographic pole of your planet, this is impossible. It means that it's not a dynamo that's creating this field. And we've observed exactly that at Saturn. Look at this Cassini probe. Magnetic axis of Saturn is aligned with the spin axis to within 0.01 degree. So it's basically a perfect alignment. And it basically directly observationally falsifies dynamo theory. So that whatever is generating the magnetic fields of planets, it's not a dynamo mechanism. Okay? I mean, at least Saturn. But if we assume that all the planets have more or less the same mechanism of magnetic field generation, then it's applicable to Earth as well. So I'll give you that. Like there's a supplementary hypothesis that I'm using here, that the Earth's magnetic field is the same as the Saturn's magnetic field in the way it's generated. Okay, then we can claim that dynamo theory is simply wrong, which means like whatever is generating the Earth's magnetic field is not the core. Like it's not this. Okay, which means we can still have a cavity. Of course, we're still left with a question like, what does generate the Earth's magnetic field? And it's a good question. Like, I'm not gonna lie, but just appreciate like these people who have detected this absolutely kind of world-shaking thing By the way, it was a big problem because in order to determine the planetary rotation period, you see, Saturn is a gas giant. You don't see anything on its surface. Like, it's very homogeneous. So you need some sort of reference to figure out how fast is it spinning. The planet itself is spinning. And people usually are using the magnetic field because it's usually not symmetrical. But in case of Saturn, it's incredibly symmetrical, as you can see. So the magnetic field basically does not rotate, okay? I mean, it appears so because it's so symmetric. And therefore, it was a big problem for determining the Saturn's spin period. I actually don't really know how they resolved it, but I mean, I remember they've claimed that they did. But just appreciate the diplomacy here in the formulation. Wait, I saw it somewhere here. Look, this symmetry prevents blah blah blah. Okay, challenges, they say. This discovery basically challenges our understanding of the MHD dynamo process. Because, again, this Cowling's theorem precludes blah blah blah, the symmetrical dynamo. It challenges, they say. I think if they would be honest, they would say it basically completely falsifies the MHD dynamo process. But I mean, there's a lot of money involved, so you cannot say that. Okay, so the magnetic field, unfortunately, does not prove the existence of the core, because again, the theory how the magnetic field is produced at the core is directly falsified by observations. Like, end of story. How exactly is the field produced? I don't know, and I don't think anyone knows, to be honest. If you know, again, welcome in the comments. Here I don't really want to talk about all of this, but let's just mention this. Okay, we've talked about the density already. Like, I just wanted to say that all of this, or at least quite a bit of what I'm talking about, depends on our understanding of gravitation. Understation of gravitanding. Anyway, and our understanding of gravitation is lacking, to say the least. Okay, so in case you're not aware, the gravitational constant is basically, we can't measure it. Like, our current accuracy is like 0.1% or about so. It's absolutely crazy for one of the fundamental constants. All right, so we have no clue how gravity works. That's basically what I'm saying. Because Newton's theory of gravity also has been directly falsified by galactic rotation. So galaxies do not seem to behave according to Newton's gravity. And in case you've been living under the rock, okay? So they've introduced dark matter to fix it, to save Newtonian gravity. So Newtonian gravity was falsified by observations of galaxies, and we're trying to fix it by introducing like 4 times more matter than we see, okay? So it's absolutely crazy, but yeah, like, you know, if you don't make such a step, if you don't say, maybe there is 4 times more of things we don't see than that we see, you're just left with a direct falsification of Newtonian gravity. So, you know, some big unknowns are here. Like, for example, shell theorem, which works in Newtonian gravity, right? It's perfectly fine if Newtonian gravity works, but it doesn't, okay? Galaxies falsify this. So, again, we're left with one big unknown, unfortunately. Okay, and now let's talk about expanding Earth a little bit. So, where does this idea come from? Wait, I have some more tabs here. Okay, yeah, this is actually very fitting. So, no pun intended again. So people have noticed that the continents align perfectly, all right? Or tectonic plates, if you wish. I would take it in air quotes. So continents align perfectly, and this supercontinent, primordial supercontinent, was called Pangaea, or Pangaea, whatever you want to pronounce it as. And some people said, wait, so, but maybe, you know, this was the Earth, you know? And the oceans did not even exist. So that was like, what, 200 million years ago, right? So maybe the oceans did not exist 200 million years ago, and the planet, like all of the sphere, was covered by continental crust. And afterwards, the planet started expanding, and so it kind of cracked the crust, and the continents started drifting apart. You know, like again, the proverbial example you use with the Big Bang illustration is to like put some dots on a rubber, how do you call it, balloon, and start inflating it. Like they would kind of move apart. And that's what kind of happened to the continents according to expanding Earth hypothesis. So I have an animation here to show you. This is what happens. So initially, supposedly, we've had only continental crust, and then as the planet expanded, the cracks started to appear, the continents drifted apart, and the oceans appeared, right? And we know, by the way, that the mantle is an incredibly huge reservoir of water. Like the mantle contains like orders of magnitude more water than we have in the ocean. So it would make sense that this water would appear, the oceanic water, because it would just appear from the mantle, essentially, okay? Because, you know, in the cracks, like these would be the places where the mantle is accessible, so the water would just pour outwards from it. So it kind of makes a lot of sense on many levels. Also, we know, you know, that the age of the oceanic crust is very small. It's up to 200 million years. So it kind of fits together, you know. So most of oceanic crust, as you can see, is like barely like 30 million years old, like all of the red stuff. So yeah, together it makes a lot of sense, and I like the idea. I think like it's really good. Okay. What about the observations again? Like we've started with hollow Earth. We said there is no direct observational evidence. Like, is the Earth expanding right now? Basically, we have like very precise satellites, supposedly. I'm gonna criticize it in a minute, which have measured that the expansion rate, if any, is less than 0.1 millimeter per year. It's the number they give you here. Let me find it. There you go. But I would claim that it's bonkers. Like it's just shit. Like you can't make this claim. Like it's impossible to measure to such precision. Like even thermal expansion, just because of, you know, daily temperature variations, would be much higher. So it's absolutely crazy to make such a claim. The satellite decay rate is kind of a chaotic process. It depends on all kinds of stuff, including the temperature of thermosphere and things like that, including solar activity, including the magnetic field motion, include all kinds of stupid crap, okay? And like to claim that you've been able to measure it to such precision is absolutely crazy to me. But there you go anyways. The claim is it's 0.1 millimeters per year. I would say that the precision is maybe 1 centimeter per year. You know, so they cannot make this claim. And again, even 1 centimeter is very optimistic in my eyes. But I'm not a specialist in this, okay? It's just my opinion. Here I'm just reporting what they report, essentially. Therefore, the Earth may expand at 0.1 millimeters per year, even currently, alright? I made some calculations. Did not prepare this segment really well, so I'll have to find it a little bit. Well, basically, what I want to say is that in 200 million years, I'm gonna link my post as well. Like this is my blog post from like almost 10 years ago, 9.5. Hopefully, you can open it and translate it in some software. So wait. What I wanted to say is that like millimeter per year is fine. Like you can actually get. Okay, let's just start with a simple thing. Like if we assume there will have been only continental crust, we can actually determine the initial radius because of this, right? Because we know the surface area of primordial Earth before expansion, because it's equal to the crustal, well, not crust, continental crust area, okay, which is roughly 1/3 of the planet's area. And if you make the calculation, you would arrive at a figure that the Earth has expanded in a square root of 3 times, okay? So the primordial radius of the Earth should have been something like 3,800 kilometers. Currently we have 6,400, okay? Which allows us to make estimates, like if this happened over 200 million years, like what would be the average, let's say, radius increase, all right? And I think I've made this calculation somewhere here, but I actually don't remember, to be honest. Give me a sec. Well, I actually can't. I actually can't find it. Let's put it this way, like a centimeter per year would definitely be enough, I think. All right, let me just not make any strong statements here, because you can can catch me by the tail, so to speak. Anyways, there is no observational evidence against expanding Earth. By the way, you can make a claim that maybe the expansion happened not linearly, so like, let's say 1 millimeter per year for 200 million years. Maybe it was like, you know, faster, much faster initially, and then it was slowing down. Then you can achieve some insane rates of expansion, all right? So yeah, the expanding Earth, I'm kind of moving to the summary, actually aligns well with a hollow Earth, obviously, because again, if the Earth is expanding, I mean, there's limited amount of matter, unless it completely like appears out of nowhere. So there should be a hole inside, right? Or at least like the average density would fall. And in case you're curious, I've just calculated once what would be like, if we had the same, the Earth have had the same mass initially, and the same density, basically, same average density, like what would be the size of the hole? And I got this figure, almost 6,000. So the Earth, if it was previously only 3.8 thousand kilometers, right now it would be, which incidentally is very similar to the outer core radius, but still, the current Earth would be basically a spherical shell with a hole as big as 6,000, okay? And us sitting on 6.4 thousand on the crust, but it's obviously falsified by the depth of the deepest earthquakes, which again happen at like 700, the deepest, I think, 660, something like this, well, 700 to round it off. Yeah. So basically, you can't just naively say, well, okay, all the density remained constant and the Earth just expanded. Like, no, it wouldn't work like this. That the density should decrease. Therefore, it would be more consistent with the current observations. So yeah. And one other, actually, the biggest, I think, issue with expanding Earth is the paleontology. Because paleontological data shows us so-called megafauna, right? Roughly speaking, dinosaurs. Well, you see, if you have the same mass as currently, like 6 times 10 to the power of 24 kilograms, if you shrink it to the radius of 3.8 thousand, the gravity would increase dramatically. Like, I don't remember, I've made some calculation here, wait. So 3 times, we've had 3 times more gravity. Like basically the G would be not 10 roughly, but 30 roughly. And this would kill even humans, I would say, right? So basically any animal bigger than, I don't know, a small mouse or something would be killed by this gravity. Yeah, I mean, unless you live in water or something. So aquatic animals would probably be fine. But no tall trees, no big animals. So yeah, the observations of the big skeletons, they definitely falsify the expanding Earth. Like this is basically the only problem really for this theory. I could have actually gone on and on. Like there's a paper, for example, which gives you a physical mechanism of expanding Earth, which is receding moon essentially. So as the moon recedes, we have the angular momentum, blah, blah, blah. But I'm not interested in this, to be honest, right now. What I'm interested right now in right now is this point, yeah. That the megafauna of the past seems to falsify the expanding Earth. And it seems to be the only thing that falsifies it, because otherwise it makes perfect sense in every respect, if you ask me at least. Okay? So, to summarize, hollow Earth is viable. If someone tells you it's not, they're stupid. I mean, the chances are they just don't know about all the evidence against the current geophysics, let's put it this way, generally. Well, maybe send them this video, by the way. That would help a little bit. And neither is expanding Earth falsified. There is megafauna which falsifies it, kind of. But then again, we have this point that, we don't really know how gravity works. So maybe the gravitation, if you shrink the current Earth to square root of 3 of its current radius, like maybe the gravity wouldn't even change. Like we don't really know. Like that's a big problem. So with this, I would conclude, okay, hollow Earth, 100% viable. Expanding Earth, maybe like 80% viable. That would be my conclusion. Alright, so hopefully you can see from what I've just shown you that there is no observational evidence that would possibly falsify hollow Earth, or even, okay, maybe there is some for expanding Earth, but not hollow Earth at the very least, alright? I mean, expanding Earth is something that deals with history, etc., etc., etc. So yeah, if you are a scientist and you say that hollow Earth is impossible because of observational data, you're just a bad scientist. I'm sorry. So there you go. And as a philosophical PS, since we are a philosopher over here, right? We are. I mean, all my sub-personalities. So, let me give you a bit of a philosophical PS. So, Sergei Perslygin, or Sergei Perslygin, the Russian thinker, modern Russian thinker, he's still alive and pretty active actually, I watch him frequently. He has this concept of a sphere. And what is a sphere? Well, I'm kind of aiming at telling you that Earth is a sphere. So we've had the concept of object in like a very old type of science, right? Roughly speaking, a single object, right? Then, like, already in the a middle of 20th century, more like a late 20th century, we've arrived at the concept of a system, for example, which is a bunch of objects and connections between them. We've also had, somewhere in the middle, in like 19th century, the concept of a medium, or if you think about ether, it was even before that, like 17th century. So all of these are like types of things, if you wish. And Perslygin, he actually mentions a couple of others, but one particular one, sorry for tautology, is a sphere. And what is a sphere? Well, one of the properties of a sphere, and why is it called the sphere? It's because most of the spheres as things are actually spherical. So one of the properties, if not even a key property of a sphere, is that it's basically impenetrable and thus unknowable, like principally. So you can never know what the sphere is about. You can only see the surface, right? So yeah, and Earth is an example of such a sphere, right? Sphere in Perslygin's terms. The sun is also a sphere in Perslygin's terms. Like basically we only see like 0.01% of it, right? And most of it is absolutely unknowable. Like we have to be kind of like, agnostics about it almost.
And hopefully this video will demonstrate to you that, well, Perislegin is right, at the very least about Earth, right? So you can come up with multitude of different models, none of which would contradict the observations, at least directly. Well, here I've demonstrated to you that the hollow Earth, for example, hollow Earth model does not contradict the observations, and it's still kind of fine, actually. All right? So yeah, Earth is a sphere. In Perislegin's terms. Maybe I should have said sphere. Alright, thank you for watching. The eons are closing.
If you wish to support me, please consider joining my Patreon. That is patreon.com/philosopher. See the link in the description. Or if you have a scientific theory of your own and you'd like my help in developing it, please join my alternative science coaching program, also available through Patreon.